will begin with lecture 1. And first of all, you must have some understanding about what we are going to do, what are the energy scales, and what are the size scales that we are dealing with. हम किस energy scale और किस size scale पे काम कर रहे हैं, वो important है. एक हमारे पास होती है atomic scale, ठीक है ना? The atomic scale, fine. And this is of the order of angstroms, right? Typically, you know, the size of hydrogen atom is in the ground state is 0.53 angstrom. So angstrom is the scale of the length, and angstrom we know is 10 to the power minus 10 of a meter. So when we are dealing with this scale of length, we are actually dealing with atomic scale, all right? Then we have this nucleus, which is at the heart of the atom, at the center of the atom. So, and the electrons, that's our picture that, you know, we have nucleus at the center, Rutherford picture, and the electrons are going around it. So, and this nucleus, the nuclear size, what we call as nuclear size, experimentally found is in femtometers, typically say around 10 Fermi, which will be around 10 to the power minus 14 meters. That is the nuclear scale. Okay. Then inside the nucleus, we have protons and neutrons, the two fundamental elementary hadrons which make up the nucleus, the particles. So their proton, as we understand, is a very stable particle, and the neutron in the free state would decay into proton and the electron or whatever. I mean positron. So this proton scale, what is this? What's the length scale here? So the scale of protons, the length scale of protons is of the order of Fermi. So it's 10 orders less in magnitude. So it is 10 to the power minus 15 meter. That would be the classical size. Okay. And then we have these protons. They are further made from quarks. Okay. And the size of the quark happens to be less than 10 to the power minus 18 meters. And our experiments can go that far only. We can only go up to quarks. Beyond this scale, the physics, of course, mathematically, we do have the concepts of strings and string theory, but experimentally, this is the final length scale we can probe, right? So we do not go beyond this scale, right? So I started from the atomic scale and I went down because I'm going to deal with the nucleus and the particles, fine. So we have atoms, जिनका scale होता है 10 to the power minus 10 meter length scale. Nuclear scale is of the order of tens of Fermi, which is around 10 to the power minus 14 meter of length scale. The protons and the neutrons have a classical length scale of 10 to the power minus 15 meters, 10 orders less in magnitude than the nucleus. And then we have quarks, which are the building blocks of the protons and neutrons. The scale is 10 to the power minus 18 meters. और उससे नीचे हमें कुछ नहीं पता है. Experiments हमारे पास कुछ नहीं है उससे नीचे. So जो हमारे सबसे बड़े से बड़े accelerators है, like Large Hadron Collider, we can only probe to the length scales of the order of 10 to the power minus 17 or minus 18 meters. Okay. Then we will be discussing energy scales. So what are the energy scales that we will be dealing with? Okay. Now in solid state physics, right? You normally are concerned with how atoms combine the energy at the atomic scale. So जो energy important रहती है यहाँ पर energy at atomic scale is more important because solids की properties जो है they are dependent on the bonds between the atoms and this bond energy जो है and that is the atomic scale energy. And how do we measure this energy? We typically know that, for example, if we take a hydrogen atom, to be more simple, the ground state energy of hydrogen atom is 13.6 electron volts, right? And in the ground state, so the energy typically would be that if you want, if you have a hydrogen atom, this is the nucleus of the atom, and that's the electron. You want to get this electron out, you need this much of 13.6 electron volts of energy. So the atoms, inside atoms, electrons are bound by energies of the order of electron volts. So electron volt is the energy scale that is relevant for atoms. Okay, so atoms have electrons bound to them, and these electrons are bound with typical energies of few electron volts, right? Now, what is basically this electron volt? What does it actually mean? So if you have two plates, right, you take two electrodes and apply a potential difference of 1 volt between them. And if you release an electron in this potential well, it would acquire an energy of 1 electron volt. All right. So that typically is 1 electron volt. It's energy gained by electron when a potential difference of 1 volt is between the cathode and the anode. So that's what we call as electron volt. Okay. So typically, if you see the wavelength of light, if you constant, that's around 4,000 angstrom to 8,000 angstrom. Okay, and one can easily calculate the energy of the photons that are associated with light, right? So the energy of the photon is h nu. We can write as hc by lambda, right? So when we use electron volts, so typically it is around 2 electron volts, 1 electron volts, 3 electron volts, depending on what is the color of the light, right? But energy of the photon of visible light is enough. So we have photons of visible light, ठीक है ना? Visible light. ये जो photons होते हैं visible light के, their energy is in few electron volts, few electron volts, could be also 0.5 electron volts, doesn't matter, but few electron volts is typical. So that energy is enough to knock electrons out from the atoms, some atoms, right? For example, in some metallic atoms where electrons are loosely bound with their nuclei, the photon can knock out an electron, famously called as photoelectric effect. Because the energy with which the electron is bound to the nucleus is some electron volts, say a few electron volts, and a photon can have that much of energy. We can impart the energy to the electron through a photon, and the photon would be released from the atom, right? So the electrons are bound in the atoms by energy scale of electron volts. How nuclei are also bound, nucleons are also bound in the nucleus. So you need energy to knock these nucleons out, right? But that energy would be in kilo electron volts. So when it comes to the energy scale of the nucleus, you see, length scale and energy scale go in opposite directions, right? The length scale goes up, the energy scale goes down. When the length scale goes down, the energy scale goes up. So this is very interesting. Fine. So we start with atoms. So we know that the length scale of the atom is 10 to the power minus 10 meter. Fine. And but the energy is in electron volts. We go down to the nucleus now, where the size is 10 to the power minus 14 meter, and the energy scale is kilo electron volts. Fine. And when we go to the particles from protons to quarks, the energies are million electron volts, then giga electron volts, and then at the quark scale, it is tera electron volts. This is the energy required. Now, this is the energy that you typically need to, you know, you play with the protons and neutrons. You want to break them, and you want to see their structure, their size. So that's in million electron volts. And when it comes to quarks, down to the quarks, the energy required are like 10 to the power minus 18 meter, which is the length scale of the quarks, would correspond to energy scale of trillion electron volts, right? So you can see the trillion electron volts is a very huge energy as compared to kilo electron volts. So nuclear physics in the sense of energy is called low energy physics. Okay. And what about atomic physics? That is very low energy physics. So because the energy scales are much lower, at least by 1,000 lower. So nuclear physics is still a low energy realm of physics. So it's still low energy physics. So, although you all know that nuclear energy is very huge, it may always mislead you that nuclear physics means high energy, but nuclear physics means low energy as compared to the energy that's required to actually do some particle physics, right? And when I say that we are doing high energy physics, so जब आप high energy physics की बात करोगे, when you talk about high energy physics, what it actually means is it means particle physics. And what it means is million electron volts to tera electron volts of energy. Although, million electron volt is also relevant to nuclear physics. But here, particle physics more relevant is around giga electron volts and TeV. See, when you talk about particle high energy physics, it is giga electron volts and tera electron volts. Nuclear physics, it is kilo electron volts and million electron volts. But still, that is low energy as compared to the high energy physics. But there's a faint, very, very thin boundary of energy when you actually go from, very high energy, very low energy. As you move in the energy scale, there is some boundary that separates them. That is million electron volt boundary. And between the atomic and nuclear physics is the kilo electron boundary that separates the two. Okay, good so far. And theoretically, if you say, what about string theory? That would need maybe trillions of electron volts, and that not achievable. So therefore, string theory people, sometimes they are criticized in physics community that they have nothing to show because such kind of accelerators don't exist. But their mathematical framework is so beautiful that we believe them. So that is how it happens. Okay. Now the question is that smaller scale would mean higher energy. So smaller scale, smaller length scale corresponds to higher energy. Why? Because if you want to see things which are very small, you need very, very high energy. Suppose you have two particles which are separated by some distance, say d, and you throw some wavelength at it, which wavelength is greater than this d, lambda is greater than d, then you cannot see that they are separated. They can be seen as a single particle. There is no way to see them as separated particles. Now, this is called the resolution, optical resolution, right? How can you see two things distinctly? Only when the distance between them is much larger than their wavelength, then you can see them distinctly, right? So, for example, I use very short wavelength. If lambda is very, very less than d, then I can see that they are two distinct particles. For example, you have two balls. Okay, they're separated by a distance of say a few centimeters. Okay, and this is say 1 millimeter in radius. This is also 1 millimeter in radius. Now, with the naked eye, we can see them distinctly. The reason is that because wavelength that I am using is say 6,000 angstroms, say mean wavelength. Okay, but that is much smaller than few centimeters. So the light, when projected on them, it will be given back, and we can easily see that there are two particles. But if the distance between them is lesser than 6,000 angstroms, then I will not be able to resolve that they are two or they are a single particle. It may appear that these two particles will appear to be a single particle. So it is very important that you use wavelength that is very small if you want to see the structure. For example, I want to see the nucleus. Fine. I will see if my wavelength is of the order of say 10 Fermi. The wavelength, I can use the wavelength of electron here. You will say, okay, radiations do not have this wavelength range, but electrons do have, because you have lambda is h by mv. I can increase the velocity of the electron, its wavelength will go down, right? I can manipulate it. So if I use electron waves to see the nucleus, suppose the electron wavelength is of the order of say 10 Fermi. I will be able to see the whole nucleus as a single particle. I will not be able to see the protons and neutrons. That's not possible. To get protons and neutrons, my wavelength must be of the order of Fermi. So I must increase the energy of the electron. So therefore, I need very fast moving, very high energy, highly energetic electrons to probe into the nucleus and to see protons and neutrons distinctly. So therefore, to give electrons that much of energy, you will need accelerators of very large size. So therefore, if I want to now see what is inside proton, naturally, and my wavelength should be much less than the size of the proton, which is 10 to the power minus 15 meter. And to reveal the quark structure, I must use very, very high energy electrons. And for that, I will need very huge accelerators. So the machines will become larger and larger as you want to probe smaller and smaller objects, right? And if I want to see a tree, I just can do it with my naked eye. So because a very small device needed to see a very big object. But if you want to go and see a proton, you need 5 kilometer maybe length of an accelerator that can actually see what is inside a proton. So what it means is that energy scale and length scales are inversely related with each other. So, okay, so naturally you will say, okay, how will we go into this smaller length scale? Naturally, how will go? We should decrease the Schrodinger wavelength, and that would need to increase the energy of the particle. And we can control the energy of the electron with the help of accelerators with magnetic and electric fields. And as we increase the energy of electrons, and their wavelengths become shorter and shorter, then we can use them as probes to see the structure of small particles. We use electrons, positrons, and very intense high energy gamma radiations for this job. Another very important thing that you should remember here once we start this course of particle and nuclear physics is that we work in natural units. So most of the times we work in natural units. So what are natural units? So particle physicists love natural units. And what do? This H cross this C, they appear very often in the equations. We set them equal to 1. So that defines a new system of units. And once we put them equal to 1, in SI system, we know they are not 1. C is 3 to 10 to the power 8 meter per second. So we know that in SI system, H is 6 into 10 to the power minus, actually 6.6 in 10 to the power, sorry, 6.6 into 10 to the power minus 34 joules second, and C is 310 raised power 8 meter per second. And we see these units, these are the SI units, right? And in natural units, we put them on. So naturally, when I put them on, I have a new way of a new system of units, and that system of units where H and C become one unit is called the natural system. And in the natural system, now we use this natural system, we have this famous equation is equal to mc squared. In natural system, E is measured in energy, and C square is unit, it's one. So M is always measured in million electron volts per C square, or million electron volts, or giga electron volts for higher energy. So this you must keep it in mind. So, okay, fine. So, okay. Okay. Now, our story begins here. So this was just introduction of the different energy scales and different length scales that we are going to deal with. And what is the physics needed to explore this scale? So what we need is quantum mechanics. And elementary course in quantum mechanics is must. Without quantum mechanics, we may not be able to do anything here. And we need a course in special relativity, which you people have already done, I think, both these courses, right? And we need some understanding of uh, electromagnetism. And I think we're all equipped with these basic structures, we already have that, we have done these courses, so there's no problem in that. I hope that you have done these courses and will be using them to explore nuclear and particle realm, to explore nuclear and particle physics. Okay. Now, how I will begin the story? So we'll go a little bit through historical background, and then we'll go and we'll talk about some very important experiments and that or that have actually opened the gates for this beautiful subject. So, कैसे start हो गया ये सारा? How did all this start? So, some historical perspective. So, there is a fellow called Henry Becquerel, right? So, what H. Becquerel? This fellow, one thing I'll show you in the insert picture. So I just so Yeah. So good. Oh, sometimes you should give me a moment because, I want to show some interesting and very important things. Okay. This fellow is Henry Becquerel. All right. So he was looking for some interesting phenomena. So he was looking at some salts, and he was placing these salts in sunlight. And he thought that sunlight would excite the atoms and the structure of these salts. At that time, there was no concept of atoms, by the way. He would say that there will be some photo-induced kind of emission. मतलब इसमें ये जब salt हम sun में रखेंगे तो ये sunlight को absorb करेगा, and then once we would place it in shadow, it will emit the radiations which it has absorbed. This was a kind of research at that time in which he was interested. It's called some sort of a photoluminescence, right? So it's where photo energies are absorbed from light and then the salts will re-emit energy. So iski खुशकिस्मती ये थी, the good luck with him was that there were rains for lots of days. मतलब जो weather था उस जगह का वो खराब हो गया. तो इसने ये जो यूरेनियम का salt इसके पास था, he put that in a drawer. So उसकी एक अलमेरा थी उसके ऑफिस में, उसने उसमें ये रखा ये यूरेनियम salt because he had to wait when the sun will shine again. Then he will put this in the sunlight and then will study the photo-induced emission kind of thing, which he believed there was something called photo-induced emission. So, but वेदर खराब हो गया तो इसने ये सारा सॉल्ट जो है ड्रायर में रखा, और उस ड्रायर के बिल्कुल दूसरे बगल वाले ड्रायर में देयर वर सम फोटोग्राफिक प्लेट्स. ये एक फोटोग्राफिक प्लेट, ये आप देख रहे हो ये काला हो गया है, ठीक है, ये खराब हो गया है, राइट. आई मीन दिस हैज एक्चुअली फोटोग्राफिक प्लेट का कलर यही होता है. ये 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 इस किस्म का कलर होता है, ये वाइट सिल्वर ब्रोमाइड टाइप कलर होता है, मतलब वाइट काइंड ऑफ थिंग, सिल्वर एक्चुअली होता है. तो जब इस पे रेडिएशन पड़ती है तो ये काला हो जाता है, इट टर्न्स ब्लैक, ठीक है. तो ही फाउंड दैट द फोटोग्राफिक प्लेट्स हैव टर्न ब्लैक. अब क्योंकि ये डार्क रूम का एक्सपेरिमेंट, ये डार्क रूम में उसने रखे थे, तो ही फिगर्ड आउट कि ये फोटोग्राफिक प्लेट्स खराब क्यों हो गई, व्हाई there is this darkness. So he thought that कि शायद ये जो iridium salt है, it is emitting the radiation that is turning these photographic plates, it is turning them black. So then he repeated the experiment. उसने आप photographic plates लाए. photographic plate होता है जो एक्सरे फिल्म आप देखते हो, जिसपे एक्सरे हम लेते हैं, वो photographic plate ही होता है, ठीक है. तो अब इसने अपने सॉल्ट्स को इसके ऊपर रखा, और then he could see that these salts are creating this distortion on the photographic plates. So therefore he could understand that even if this salt is not exposed to light, without actually exciting it, if you have this uranium salt which has uranium in it, then it is naturally giving out radiations without actually by any excitation due to heat or light. It is capable of giving out these radiations. लेकिन उन दिनों atom का कोई मतलब नहीं था, because atom was not discovered, and those days we did not have any understanding of particle physics. So, but the experimenters did show that there are 3 types of particles coming, and they were not knowing what is the nature of those particles. तो इसलिए उन्होंने उसका नाम अल्फा बीटा गामा रखा, because they were not knowing what they are. So that's why ABCD, आप उसका नाम रखो, आपको पता ही नहीं है वो क्या होता है, तो अल्फा बीटा और गामा उन रेडिएशंस का नाम रखा गया। और उसके बाद लोगों की इंटरेस्ट इसमें आ गई। देन आफ्टर Becquerel, Henry Becquerel, once he discovered radioactivity, people, naturally scientific community got interested that there are, so he concluded that there are some materials like the ores of uranium, some materials which are radioactive. What does it mean? That these materials, uh, they emit radiations, and these radiations, he did not know the nature of these radiations. So, but one could figure out that there are three types of them. So they were named as alpha, beta, and gamma. So this became a very important research in around 1890s or 80s. So 1890s, and this became very important area of research to study naturally occurring radioactive materials. Then, it was Madame Curie people and others, they further could see some other materials, like radium was seen by Madame Curie. So there were other materials like polonium was also seen to be radioactive, that there were many naturally occurring materials which were radioactive. And they, like radium was giving weak alpha particles. Weak alpha particles were emitted from this radium, and Curie was able to extract radium from pitchblende, and then they also discovered polonium, and then there were many other materials which were discovered were radioactive. So this was very interesting era of research. Then in around 1909 and 10, during this time, Morrison and Geiger, these are the two students of Rutherford. Rutherford tells them that, recently people have been very much interested in radioactivity. So what you do is you take radium, which is a source of alpha particles, and you try to figure out and take thin sheets of metal. And they could take very thin sheets of gold and thin sheets of metal and see the effect of these alpha particles, and try to see how many particles are getting through or if there are any deviations. So this is how Rutherford's experiment was set up. And these Geiger and Morrison were the two people who were involved in this job. So then we will discuss this Rutherford scattering experiment in our next lecture, and we will go into the mathematical details of this experiment, and we'll try to understand it historically and how important breakthrough it was. So I think today's lecture I would end here. So we will begin our next lecture from Rutherford scattering. And if you have now any questions, we can ask.
Yes, sir. So, out of curiosity, I wanted to ask that quarks, the elementary particles, what experiments are the ones proving that the existence of quarks?
This is an interesting question in the sense that we have not actually been able to isolate quarks. Even today, we have still not isolated quarks. But the properties of most of the properties of the particles have been mapped, have been observed. And it turns out that quarks is a very well established theory, and it still is theory, because you do not have free quarks, right? But the quark model does explain the existence of the particle creation For example, if I have a proton and I want to snatch its quarks, the other kinds of particles get created. The creation of those particles is very well explained by the quark model.
So then there is no experimental proof of the existence of quarks. Be it not, let's say, we don't want to see a single quark. We want to see a bunch of quarks. Then for the bunch of quarks, do we have seen in any experiment?
There is quark gluon plasma. Now, it is, people see these, unless you don't have an isolated quark and you don't find its properties, in principle, you can say it doesn't exist. So you see, this is a very interesting story. You pointed out something very interesting. I mean, chemistry people believed in atoms before physics people believed, because in chemistry people knew that there is the law of proportions of law of combinations, right? So when you take some material of some object and when you mix two materials, they mix in some interesting proportions. And this led early chemists to believe that it is only possible there is something very elementary which cannot be divided further. They call it atoms. When physics people were asked, do atoms exist or not, they answered in a beautiful way that they said that, if you cannot observe something, if you cannot measure a physical property of something, then to talk about it is nonsense, right? So, physics people did not accept atoms unless the discovery of unless the paper by Albert Einstein on the Brownian motion, he was able to calculate the size of the molecules of the water through the motion of the pollen grains. So that was the first time, the atom was revealed to physics people, that there is something very elementary at the fundamental level. But it was the exploration by Rutherford's experiment that really we went into the heart of the atom and figured out what is actually made of. But similar is the situation right here, right? We do have the beautiful physics that is coming at elementary particle level, but we have not been, as far as I understand, we have not been able to isolate a single quark. But we know that they exist in structures, and their explanation is their properties are explainable only if we believe that the quark model is correct.
So, sir, you mentioned one statement that string theory comes after quark. Like after the quarks, we study string theory. Quark is the smallest one, and after that, if we go to the smaller scale, we go to string theory. So, is it so?
Yes, basically, not only quarks, actually, when we will go to the particle physics, we'll see that there are three kinds of truly fundamental particles: quarks and leptons, and photons, right? These are the truly fundamental ones, and quarks and leptons and photons, of course. Photons, I will say, a different kind of structure, because photon is massless. It is not interacting with Higgs field in that sense. That when there are massive photons like gravitons but they have some mass. They do interact with Higgs. And this looks very technical kind of. Leptons are not made of quarks. Leptons are the truly fundamental particles, like the electrons are leptons, to be very straightforward at this point of time. And quarks, of course, they are the fundamental structures of hadrons, like protons and neutrons are made of quarks. Now, what if our scale of length is beyond this, right? If we go down to say 10 to the power minus 25 centimeters, or maybe we go to Planck level, Planck scale, we go to really, very
the smallest level,
smallest possible level, then the energies would become fabulous, right? Then the explanation, you can actually do some theory, It's maybe that you don't have experiments right now, but theoretical physicists believe that there could be experiments, in future. And But how would physics, see, physics theories are scale dependent, right? Right, you go from classical and you go to scale of quantum mechanics, the classical mechanics fails. Now, then you go to the Planck scale. What happens then? Right? Does quantum mechanics actually fail? So at Planck scale, we can see that there's a merger of these quantum mechanics and gravity. This is what theoretical physics people believe. So it becomes another interesting realm. But again, the question is that, does it really make sense? If you ask technically to a physicist, he would say that there will be two schools of thought. One school who do lots of mathematics, they will say the mathematics is so beautiful that it has to be correct. And if people have not found it, it is not our problem. Maybe the generations in future will figure it out. They will have enough machinery to see at the scales, say down to 10 to the power minus, say 30 centimeters. But right now, we don't have energy scales of that level. Does not mean we should stop doing physics. So this is what string theory, is motivated to. They do physics, but they do not have experiments to support them. But a person who is more experimental in nature would say you that this is wastage of time. If you cannot measure something, then talking about is useless. Right, so because anyway, physics is a science, and we must have something. We are talking about something that's out there in the nature. Just no, we don't have. You are talking of something I cannot verify. So I mean, how can I accept it as science? So it's
Yes, sir.
pure mathematics. Yeah.
So there's a chain of thought like classical theory fails at quantum level, and quantum theory like fails at let's say string theory level.
No, actually, there is a single theory. Like quantum theory does not fail at classical level. The point is that quantum mechanics will go to classical mechanics as you approach, like your energies become of the size of classical domain. Your scale becomes class. Quantum mechanics will give you all the results that classical mechanics also gives you, right? Because finally quantum mechanics comes down to Newton's second law. There is something called
Yes, sir. Yes,
Erwin-Hassel's
sir.
theorem, right? So it doesn't fail, but it's a better theory than the classical theory. Okay.
No, sir. Actually, I was saying like classical is a special case of quantum. We say
Yeah, we are looking for a theory whose quantum is special case of that theory. We are actually looking for a more unified, a kind of a
yes,
model,
yes,
more unified theory,
yes.
right? Where gravity, all these theories would merge into a single theory. That's what
Okay, sir.
actually we are looking, technically speaking. Any other person to ask questions? Yes. Nobody else. Others can unmute, or I have to mute all. What I have muted them, or what is the problem?
No, sir. No, sir.
They have
They
muted
can
themselves.
unmute and ask.
Yeah, so that's what. I have not muted all. They can unmute and they can talk.
If
So
anybody has any question, you can ask.
yeah, and take the screenshot of all the participants, because the attendance has to be kept and sent to director each day. So that's what I am told, that you monitor the attendance of the students, because
Okay, sir.
this way it gets a very organized kind of teaching learning. If the students come and they attend classes regularly, this will become more organized kind of teaching learning process.
Yes, sir.
Okay, then I think today's lecture was of introductory level, and will be more mathematical in our coming lectures, but it was very important. Any queries will be always very much accepted, and I have not gone into the particle physics depth because that would be taken after nuclear physics. And first of all, we'll try to understand nuclei and their properties. We'll start from the historical scenes of discoveries, and we'll talk about mathematical, for example, in my next lecture, I'll be talking about Rutherford scattering. Although that is not in the syllabus, but it's very important.
Yes, sir. Yes, sir. So we will be following crane.
No, you will be following all these books depending on what I'm doing. So,
Okay.
for example, this scattering, nobody does it better than Ashok Das and Fribble and Das. This is the book. This is one of the best books. I'll show you this book. So, Fribble and Das. So,
Okay.
it is by World Scientific, I think. If I'm not wrong, yeah, it's World Scientific. This World Scientific is one of the very renowned publishers. So our most of the research papers go to World Scientific. So this you can see this. Are you able to see what I'm scrolling?
No, sir. Actually, you are sharing only OneNote window.
Okay.
You
Yeah.
have to share desktop.
Okay. Yes. So no need. I will share desktop. I want to show you this new share. Okay. So okay. Okay. Now is it clear?
Yes, sir. Yes, sir. Now we can see the book.
Yeah, so now you can see the book because this book, Introduction to Nuclear Physics by Das and Furble. So Furble and Das, this is one of
Okay.
the very important books in nuclear physics. This is the book, it's World Scientific, right? New Jersey, London, Singapore, and other places it's printed. So, and then Das and Ashok Das has really written some very good books. Our students and teachers. We apologize. University of Rochester, 2003 is it's a very fresh book because nothing much has happened in nuclear physics in the last 50 years. So that way it is written in 2003, so it's very fresh. So
Okay, sir.
Rutherford is although during my PhD I did some work in nuclear physics only. So, but I learned that the excitement in nuclear physics is not that much now. People are interested in other things. So Rutherford scattering is this is a very important topic. The reason of its importance is historical reasoning only, and then we'll go to nuclear phenomenology, nuclear models. These are very important. Then some decaying processes. Yes. Accelerators and all that. Then this is that elementary particle physics. So most of it is covered here actually, and most of the syllabus.
Okay, sir.
Okay, and you will also need other books if you like. No, the other books I've given, they're also very important. I think we must stop now, and I will end
Okay,
the
sir.
meeting. So, okay.